What if everything we know about the universe is fundamentally wrong? Not slightly inaccurate, not unfinished, but broken at the deepest level. For over a century, physics has relied on a framework called the Standard Model. It predicts particles, explains stars, describes matter itself, and for a long time, it worked beautifully. But when we started looking deeper into the universe, something unsettling happened. We began finding things that shouldn't exist. Galaxies that formed too early, black holes that grew too fast, structures too large for gravity to build. It's like discovering rooms in your house that were never on the blueprint. Rooms you didn't build. Rooms that shouldn't be there. These aren't fun mysteries. They're structural failures. They suggest that our understanding of reality has cracks running through it. And those cracks are growing wider with every new observation. To understand how deep the problem goes, we need to start at the beginning, with the first structures that broke cosmology. When the James Webb Space Telescope sent back its first images, astronomers weren't celebrating. They were confused, then concerned, then quietly alarmed. Webb was designed to see the universe's first galaxies, cosmic infants, small, chaotic, still forming. Instead, it found giants, massive spiral galaxies, existing just 300 million years after the Big Bang. That's 3% of the universe's current age. To understand the problem, imagine planting a seed and returning an hour later to find a fully grown forest. Physics says that's impossible. Gravity needs time. Matter needs time. Stars need time. But these galaxies didn't wait. Some contain billions of stars, fully formed, already structured. And they aren't rare. There are dozens, possibly hundreds. Each one silently asks the same question. How did they grow up? Before the universe allowed them to? At the center of many impossible galaxies lies something even worse. Supermassive black holes. In today's universe, these giants grow slowly, over billions of years. There is a limit to how fast they can feed. As matter falls in, it heats up and pushes back. It's called the Eddington limit. Even at maximum speed, a black hole starting small cannot grow this large in time. But we've found black holes over 1 billion times the mass of our Sun, less than 700 million years after the Big Bang. The math doesn't work. So physicists propose something radical. What if entire gas clouds collapse directly into black holes? No stars, no waiting, just instant monsters. The theory is possible, but only under extreme conditions. That shouldn't be common. Yet these black holes are everywhere. Ancient, massive, and completely ahead of schedule. Time, it seems, was cheated. Cosmology rests on a quiet assumption that on large scales, the universe is smooth. Zoom out far enough, and everything evens out. This idea is called the cosmological principle, and it predicts a limit beyond a certain size. Structures shouldn't exist. Then we found the giant arc, a crescent of galaxies, stretching 3.3 billion light-years, nearly 3 times larger than theory allows. It's like finding a mountain range wrapping around a planet, and it's not alone. We've found other colossal walls of galaxies, each one too large, each one a violation. If these structures are real, then uniformity breaks. And if uniformity breaks, The foundation of modern cosmology goes with it. Here's a simple question. How fast is the universe expanding? For decades, cosmologists believed we had the answer. In fact, we had two ways to measure it. They should agree. They don't. One method looks backward, to the afterglow of the Big Bang, the cosmic microwave background. Using our best models, it predicts the COM expansion rate, 67 kilometers per second. The second method looks nearby, at stars, at exploding supernovae. It measures how fast galaxies are moving away right now, 73 kilometers per second. That gap may sound small. In physics, it's enormous. The odds of this being a mistake are less than 1 in 3 million. Both measurements are precise. Both are trusted. And both cannot be right. This is called the Hubble tension. It suggests something happened between the early universe and now. Something we don't understand. And the more accurately we measure it, the worse the disagreement becomes. Physics relies on constants, numbers that never change. One of them controls everything you see. It's called the fine structure constant. It determines how tightly electrons bind to atoms, how chemistry works, how light behaves. We've always assumed it's the same everywhere. But when astronomers studied ancient light from distant quasars, they noticed something disturbing. The absorption patterns didn't match. In one direction of the sky, the constant appeared slightly weaker. In the opposite direction, slightly stronger. It's as if the laws of physics have direction. A cosmic gradient. If this is real, it breaks a core assumption of relativity, that the laws of nature are the same everywhere. It would mean the universe has a preferred orientation, an axis, a structure we never expected. And if one constant can vary, what else can? In the universe's first minutes, everything burned. Protons and neutrons collided. Hydrogen formed. Helium followed. And a trace of lithium. We can calculate exactly how much should exist. And for hydrogen and helium, the math is perfect. But lithium doesn't match. We predict 3 times more than we observe. 2/3 of it is missing. It's not hidden. It's not destroyed by stars. We've checked every known explanation. Some physicists suggest unknown particles destroyed it early. Others think our nuclear models are incomplete. But the real concern is deeper. If we're wrong about lithium, what else did we get wrong about the first moments of reality? Most of the universe is invisible. 85% of all matter doesn't emit light. We call it dark matter. Without it, galaxies should fly apart. Stars orbit too fast. Something unseen is holding everything together. We've built detectors, buried them underground, smashed particles at near light speed, and found nothing. Every experiment comes back empty. Then there's another problem. Our simulations predict thousands of small galaxies around the Milky Way. We see about 50. And in 2018, we found something worse. A galaxy with no dark matter at all. Its stars move exactly as expected. From visible mass alone, dark matter exists. But we don't know what it is, where it hides, or why it sometimes vanishes.
Empty space is not empty. According to quantum physics, space is alive with activity. Particles appear and vanish. Energy flickers in and out of existence. We can calculate how much energy should exist in empty space. Then we measure the universe and see how fast it expands. The numbers should match. They don't. The theoretical prediction is larger than the observed value, by a factor of 10 to the power of 120. That's not an error. That's the worst prediction in the history of science. If the calculation were correct, the universe would have exploded instantly, or collapsed before anything formed. Yet here we are. Something is canceling almost all of this energy, perfectly, to 120 decimal places. We have no idea what it is. This isn't a small mistake. It means our two best theories, quantum mechanics and gravity, cannot both be right, especially when describing nothing. There are hundreds of billions of stars in our galaxy alone. Many of them have planets. Some of those planets are habitable. By probability alone, intelligent life should be common. So where is everyone? When we listen to the universe, we hear nothing. No signals, no structures, no visitors. This is known as the Fermi paradox. In 1977, one signal broke the silence, a powerful radio burst detected at hydrogen's frequency. It lasted 72 seconds and appeared artificial. It became known as the wow signal. Scientists searched again. For decades, the signal never returned. Since then, the universe has remained silent. There's a disturbing explanation for the silence. Imagine the universe as a dark forest. Every civilization is a hunter. Resources are limited. Survival is uncertain. You can never know whether another species is friendly or a future threat. In this scenario, the safest strategy is silence. Hide, stay quiet, and if you detect another civilization, you eliminate it before it can eliminate you. The universe isn't empty. It's quiet because everyone is hiding. Every signal is a risk. Every broadcast is a flare. Once you're seen, you don't get a second chance. There is another possibility, even more unsettling. Somewhere between lifeless matter and galaxy-spanning civilizations, there is a barrier, the Great Filter. A step so difficult that almost no one survives it. The question isn't whether it exists. The question is where it is. If the filter lies behind us, then life or intelligence is rare, and we are lucky. But if the filter lies ahead, then something destroys civilizations after they become advanced. War, climate collapse, runaway technology. The silence of the universe may not be emptiness, it may be a warning. If we ever discover the remains of an advanced civilization, it would be the worst discovery imaginable, because it would mean they reached our stage and still didn't make it. The universe is not loud. It does not announce itself. Between galaxies, there is no sound, no signal, no echo, only silence. When we point our telescopes outward, we expect noise, civilizations, signals, proof that we are not alone. But the universe remains quiet. This silence has a name, the Fermi paradox. In a universe with hundreds of billions of galaxies, each containing billions of stars, logic suggests life should be common. And yet, we hear nothing. No messages, no beacons, no cosmic conversations. This silence forces a question more unsettling than loneliness. What if advanced civilizations do not last? What if intelligence is rare not because life is rare, but because survival is fragile? Perhaps civilizations destroy themselves before they can reach the stars. Perhaps they choose silence to avoid being seen. Or perhaps we are early, listening before the universe has learned how to speak. The silence does not answer us. Imagine the universe as a dark forest. Every civilization is a hunter moving quietly through the trees. No one knows who else is out there, and no one knows their intentions. In such a forest, revealing your position is dangerous. This idea is called the dark forest hypothesis. It suggests that intelligent civilizations stay silent, not because they are absent, but because survival depends on invisibility. In a universe where technology grows rapidly, the first to detect another civilization could eliminate it before it becomes a threat. Not out of hatred, but out of caution. In this scenario, silence is not loneliness, it is strategy. Signals are not invitations, they are vulnerabilities. Every transmission risks annihilation. If this is true, then the quiet universe is not empty. It is watching, waiting, and choosing not to speak. The question then becomes unsettling. If everyone is hiding, should we be announcing ourselves at all? Somewhere between simple matter and cosmic civilizations, there may be a barrier, a filter, the great filter. It is a stage in evolution that most life never passes. Perhaps life rarely begins. Perhaps complex cells are rare. Perhaps intelligence is uncommon. Or perhaps the filter lies ahead of us. Nuclear war, runaway technology, artificial intelligence, environmental collapse. If the great filter is behind us, then humanity is extraordinarily rare. But if it lies ahead, then our future is fragile. The universe may be filled with civilizations that reached our level and went no further. Not because they failed to explore space, but because they failed to survive themselves. The great filter does not need violence. It only needs time and mistakes. And if this filter exists, it means the universe is not hostile. It is indifferent.